Welcome to the Explainer. So, if you've been using AI to generate your R code, you have definitely experienced that amazing high when it works perfectly on the very first try. It feels like magic, right? But I'm guessing you've also felt that absolute sinking feeling when it suddenly throws a massive wall of angry red error text at you, and you literally want to throw your laptop straight out the window. Well, today, we're going to fix that. Our goal for this explainer is to move you from being an insecure code copy-paster to a completely confident, in-control R practitioner. We're going to build a solid mental model of how R actually thinks. Because here is the million-dollar question. AI wrote your R code, but do you actually understand it? Relying entirely on an AI-generated script is honestly pretty dangerous. Why? Well, because while AI is incredibly fast, it completely assumes you know how to supervise it. If you are just blindly copying and pasting a 50-line script, you are inviting silent, invisible errors into your data. You could literally end up dropping half the patients from a clinical dataset without even realizing it, or entirely misinterpreting a chart because the underlying data was just fundamentally misaligned. To fix code, you have to be able to read code.
So to get you reading code fluently, here's our quick roadmap for today. First, the R mental model. Second, the anatomy of a data frame. Third, transforming and cleaning data. Fourth, visuals and statistics. And finally, we'll lock in an AI-safe R workflow. Let's dive in.
All right, Section 1, the REN mental model. Let's get your workspace organized.
Okay, the first thing to know is that in R, literally everything you create is an object. Think of it like a named container that holds your information. Whether it's just a single number, a list of patient names, a massive dataset, or even a complex statistical model, they are all objects. And here's the kicker. If you don't explicitly save your data into an object, R immediately forgets it the split second after it calculates it.
So how do we create those objects? We use the assignment operator. It looks like a little left-pointing arrow, just made out of a less than sign and a dash. When you're reading AI-generated code, you want to read this arrow from right to left. It translates to store this result into this container. So in a standard script, it's saying, use the read CSV function to read your patient file and store that resulting data into a container named patient data. Boom, that's it. That right there is the core sentence structure of the entire R language.
To really make this click, think of R as a master chef and RStudio as your kitchen. The chef absolutely knows how to cook, but they need an organized workspace, right? First, you have your project folder. That's the physical kitchen where all your work lives. Inside that, you have your script file. That's your recipe, the step-by-step code you or the AI wrote. Then you have your data file, which are your raw ingredients. And finally, your output, the finished meal, like a beautifully plated chart or a clean data set. If your recipe is looking for ingredients in the wrong kitchen, yeah, your code is going to fail. Always keep your scripts and data inside your designated R project folder.
Now, here's a massive stumbling block for beginners: packages. Base R is your default kitchen setup. It's got a stove, a couple of knives, but if you want to do advanced data cleaning or make those really beautiful charts, you need specialized appliances called packages. Here's the trick to understanding them. Install.packages is like driving to the store, buying a blender, and putting it in your kitchen. You only have to do that once. But the library command, that is like plugging the blender into the wall. You have to do that every single time you walk into the kitchen, or in this case, open RStudio and want to use it. AI scripts often throw both commands at you, but remember, you only install once per computer.
Moving right along to Section 2, Anatomy of a Data Frame. Let's talk about tables.
Once you actually bring your data into R, it almost always takes the form of a data frame. Now, a data frame looks a lot like an Excel spreadsheet, but it is strictly regulated. I mean, in Excel, you can type a word into a column full of numbers, and Excel doesn't blink an eye. R, on the other hand, cares deeply. A data frame is a collection of vectors, or columns. And the absolute golden rule is that every single item in a specific column must be the exact same data type: numeric for numbers, character for text, logical for true and false, or factors for strict categorical data.
Think about a perfectly clean clinical dataset. Age and CRP levels, those are strictly numeric vectors. Sex is a character vector. And a column flagging high CRP is a logical vector, just true or false. If you accidentally have the word missing typed out in your numeric CRP column in your raw data file, R is going to force that entire column to become a character vector, and suddenly you can't calculate an average anymore. It's frustrating at first, but this strictness is absolutely a feature, not a bug, because it prevents really sloppy math.
But wait, what actually happens when you are legitimately missing data? In R, that's represented as NA, not available. And please, hear me on this. NA is not 0. NA is a black hole. If you ask R to calculate the average age of a group and there's an NA hidden in there, the answer R spits back will literally just be NA. Why? Because mathematically it can't know the true average. AI scripts constantly forget to warn you about this. You have to explicitly tell R how to handle these black holes, usually by adding a little command to just ignore them during the calculation.
Okay, on to section 3, transforming and cleaning that data.
Real-world data is never perfect, so we have to manipulate it. When you look at AI-generated code, you are going to see the $sign everywhere. The $sign is R's extraction tool. It basically says, hey, go into this data frame and pull out this specific column. Reading right to left, a common line of code might say, take the CRP column inside patient data, check if each value is greater than 10, and assign that true or false result into a brand new column called high CRP, inside that very same patient data object. It's a really elegant way to create a new variable based on an existing one.
For the heavy lifting, though, your AI is almost certainly going to use the dplyr package. You absolutely must memorize these core verbs because they will be 90% of your daily work. Filter is for rows, like filtering to keep only male patients. Select is for columns, like keeping only the ID and age columns. Mutate creates brand new columns or alters existing ones. And summarize collapses your data down to calculate things like averages. Your AI might also throw in verbs like left join to stitch two completely different data frames together. When you read an AI script, hunt for these verbs. They tell you the actual story of how your data is being transformed.
Oh, and this brings us to a concept that completely frustrates beginners: wide versus long data. Look, humans love wide data. We like seeing patient 1 on a single row, with nice, neat columns for baseline, week 4, and week 8. It makes sense to us. But our plotting tools, they absolutely hate wide data. R prefers long data, where every single measurement gets its own separate row. So patient 1 would actually take up 3 separate rows. If your AI gives you code using the tidier package to pivot your data, don't panic. That's just it restructuring your human-friendly table into an R-friendly format so you can actually build some charts.
Which perfectly transitions us to section 4, visuals and statistics. Let's talk about ggplot2. R is famous for generating those gorgeous publication-quality graphics, and it mostly uses a package called ggplot2. Now, the code for it looks incredibly intimidating at first because it uses all these plus signs to add layers. But honestly, it always follows a strict 3-step grammar. First, you declare the data. Second, you define the aesthetics, which is just a fancy way of mapping your columns to visual elements, like saying age goes on the x-axis and CRP goes on the y-axis. Third, you add the geomes, which is the actual geometry you want to paint on the screen, like scatterplot points or a bar chart. Once you see that 3-layer structure, the intimidating code suddenly makes perfect sense.
And when those 3 steps, the data, the aesthetics, and the geometry, are combined properly, boom, you get a clean, highly customized visual, like comparing average CRP levels across different treatment groups. And the best part is, you can easily tweak the AI code to change colors, titles, and themes simply by adding more layers to the bottom of that ggplot block.
But of course, before we make things pretty, we usually need to understand the underlying numbers. Using that summarize verb we talked about earlier, we can group our patients by their treatment and then calculate the count, the mean CRP, and the standard deviation for each specific group. This basically builds out the descriptive statistics for Table 1 of a research paper. And from here, your AI can easily generate the code for formal statistical tests, like a t-test to compare 2 groups, or a chi-square test for categorical data, just to prove if those differences you're seeing are actually statistically significant.
And finally, section 5, the AI-safe R workflow. Let's talk about avoiding those silent errors.
Okay, so we've built the mental model. Now, how do we put this all together so you don't get burned by a hallucinating AI? Blindly copy-pasting means dumping a huge block of code into your script, hitting run, and just praying it works. This creates a really dangerous illusion of competence. The AI-safe workflow, on the other hand, requires discipline. You need to ask the AI to explain the logic of what it wrote. You run the script line by line, not all at once. And most crucially, you have to inspect your data frame after every single data manipulation step, just to prove the code actually did what the AI promised it would do.
To do that inspection, you must use these core functions. Think of them as your flashlights in the dark. Use class.dot to ensure R actually sees your data as a data frame. Run head.dot constantly to print the first 6 rows and visually verify your changes.
Use summary dot to quickly spot those dangerous NA black holes we talked about. Use names dot to check your column spellings because remember, R is strictly case sensitive. And use ls dot to verify what objects are actually sitting in your environment. If you use these flashlights after every major step an AI script gives you, I promise you will catch 99% of errors before they snowball into a nightmare.
Which brings us to the end of today's explainer. I want to leave you with this final thought. Will you run your next AI script blind, just hoping for the best? Or are you going to break it down, inspect the objects, check the data frames, and read the code step by step, exactly like a master chef reading a recipe? Take control of your code, apply this mental model, and your R skills are absolutely going to skyrocket. Thanks for hanging out with me on this explainer, and hey, happy coding!